A supplemental section 6.5 in the textbook does an excellent job explaining the Copenhagen interpretation of quantum mechanics. And it's a good idea to read through that in prep for an essay. Another way of explaining that interpretation of quantum mechanics was proposed by Erwin Schrödinger, and it's you've probably heard of this before. It comes up in popular culture quite a bit. Schrödinger's cat. And we're going to go ahead and watch this video in class together on the next time that we meet, because I think it'll fuel some discussion on what some of this means. The idea here that we're going to get from the textbook, from Copenhagen, from Niels Bohr, from Erwin Schrödinger and his cat, is this idea that the act of measurement plays a central role in the outcome of an experiment. That measurement inherently changes the system. The system's state is dependent on being measured. Einstein hated that. It was part of the reason why he could not embrace quantum mechanics for the bulk of his career. He got in very public arguments, not angry arguments, but disagreements, cordial disagreements, with Niels Bohr and the other quantum mechanics folks over this. Really with all of the quantum mechanics folks, but Niels Bohr was the one who had the courage to stand up to him. For the last 80 years, scientists, theorists have been trying to formulate a model of nature, beginning with Albert Einstein, trying to formulate a model of nature that is observer-free, where we can predict or calculate quantities without the insertion of an experiment, without the insertion of an observer. And they have been grossly unsuccessful in this attempt. Another consequence of the Copenhagen interpretation of quantum mechanics, another one that Einstein did not get along with, is this idea called quantum entanglement, or in German, Verschränkung. When particles interact physically and then become separated from one another, the type of interaction is such that each resulting member of a pair of particles is properly described by the same quantum mechanical description. In other words, they are both described by a single wave function, and that wave function is indefinite in terms of important factors like position and momentum and spin and polarization. In other words, that wave function is not determined in any of those factors because the measurements haven't taken place yet. But because of the type of interaction between these particles, they are found to be described by the same wave function. They are entangled with one another in a quantum mechanical way. So the state of each particle is indefinite or undetermined until one particle is measured. And measuring one particle defines that state, defines those parameters for the other as well as for the one that was measured. So therefore, until a measurement occurs, the wave function of each is a superposition of the wave functions of the possible outcomes of the measurement. But once the measurement is taken, once the measurement occurs, the wave function collapses down to one eigenfunction, but it collapses down to one eigenfunction in both places that those two entangled particles exist. Einstein had a bigger problem with this perhaps than he did even with the rest of the Copenhagen interpretation, because the effect of that theory is that measurement at one point in space caused an instantaneous change or determination to the wave function at another point in space, which means information is traveling from the position of the one particle that's being measured to its entangled particle that's at some distance, without passing through the space in between. It's traveling at an infinite speed. And in Einstein's mind, that violated the theory of relativity. It violated the speed of light maximum for any information to travel. And he referred to this in English as spooky at a distance, in German as Spuktafe Fernwirkung. And it was a big problem that he had with the Copenhagen interpretation of quantum mechanics. Now, an example of quantum entanglement, and there, like I said, there's still some argument as to whether this is true, but an example would be if we had a laser beam, so a beam of photons passing through a nonlinear crystal. That nonlinear crystal could split a photon into two equal photons of smaller energy, smaller momentum, and their momentum and their energy would add up to the momentum and energy of the original photon, but they would be traveling now in different directions at a particular angle to one another, but they would still both be described by the same wave function. They would be entangled, or they would be Verschränkung. And like I said, Einstein doesn't want to believe that this is the case. If one of these new photons is passed through a double slit and then onto a detector, it will exhibit the expected diffraction pattern. The problem for Albert Einstein is that this experiment was done and the other photon that wasn't passed through this double slit also exhibited the diffraction pattern on a detector. And these detectors, these photons, were 10 kilometers apart. The mechanism for why this happens experimentally is not at all yet well known. There are some theories in use, but it's a proof that Einstein was wrong about his problem with spooky at a distance, or Spooktafe Verwirkung. Particles that are entangled communicate with one another from a distance and instantaneously. And so one of the words that scientists use to describe this is the idea that the information has been teleported. The textbook describes in the final section of this chapter how, in theory, the idea of entanglement can be applied to computing to create a quantum computer that could store information, and instead of storing it as bits, where each piece of information is either a 1 or a 0, it would store them as quantum bits, or what we'll call qubits, where each piece of information is a linear combination of 1s and 0s. And so you have the possibility of computing with orders of magnitude more power than you do just using bits, just using two possibilities for each bit of information. These computers haven't been experimentally or physically invented yet because of difficulties in generating and maintaining unstably entangled particles when exchanging information with them. I do want to explore this concept a little bit further, and so right now I'm in the process of assembling the equipment we would need to build a detector, to build an instrument that would handle entanglement, that would detect or prove or verify entanglement for a particular particle. We're going to stick with photons, but lab number 8 is going to be a lab hopefully that will confirm the idea of entangled photons. And the way that we're going to do this lab will be outlined in the lab manual online. But photons aren't the only particles that can be entangled. There are experiments going on in chemistry and physics for entangling particles as large as atoms and even as large as fullerenes, having their quantum mechanical systems overlapped or entangled with one another even when they exist at a distance. In class or during the lab, we'll discuss ways around Einstein's objection to faster than speed of light transfer of information. But what it gets down to is assumptions in Einstein's theory of relativity that he would admit while he was talking about other things. Assumptions that aren't necessarily true or false, but that he made to make his math easier, that could easily have been assumed differently and accounted for this phenomenon without any violation of relativity. So we'll talk about that a bit more in class and in the lab. I find this to be one of the more interesting quantum mechanics topics, so I encourage you to read up on that as you find interest.